Good morning, everybody. We finally have a projector, so I think I can start. My name's Halvar. I'm a reverse engineer for a German company called Cybersecurity. We specialize in obscure reverse engineering tools for niche markets. And yeah, I'm going to give a talk on what I think are the issues that we as reverse engineers should try to solve. So in general, this talk is very different from from all the talks I've given so far, because I will not have really much to show. Like, I won't have any tools that work or any bugs that work or whatever. Basically, yeah, I won't show any cool bugs. I'm getting old, I'm losing hair. Bugs get fewer, hair gets fewer. So I can't really disclose that sort of stuff anymore. I don't really have solutions to any problem in this talk. So this talk is essentially a wish list of things that I think are solvable and that I would like to see solved. And for most of the problems that I will be discussing here, I'll give a vague and most likely incorrect idea on how that could be done. And yeah, so it's basically I'll be dumping a bunch of ideas that are all half-cooked and not well thought through to the audience, and hope that a few of you will pick them up and think them through and tell me I was wrong and show me a good solution. So, before we start talking about reverse engineering, we should probably start understanding the concept of engineering. And what is engineering really? Because reverse engineering is the inverse process of that. So, yeah, in engineering you have a problem which you would like to solve, and then you design a system and its components and how they interact. And then after you've designed that, you either construct the components or you steal them or you do whatever with them, and you string it all together. And in the end, you integrate it all and hopefully it works and doesn't collapse. Yeah, so the thing is that we start with a very abstract design or an abstract idea, and then we have a concretization that ends up with a source code. So the source code is really the last step in the entire engineering process. All right. Now, all of us have been involved at some point in some engineering somewhere, and we all know that engineering in practice is not as clean as I just described it is. In essence, you, in many cases, just tie things together and weld them together somehow so that they fit. That doesn't really change that there is an implicit design in source code or in the code that you have in the end. So it might not actually reflect the design you have on paper or the design you have in your head or the design that you should have, but in the end, the code that you have has an implicit design. And also the code that you have in the end is implicitly modularized, meaning there's components of the code responsible for one thing, there's components in the code responsible for another thing, and those are actually separate in the source code somehow. And you have trust relationships which are either explicitly modeled in the design or implicitly there in the code. And oftentimes your code will not reflect the trust relationships you had in the design phase. And yeah, so there's a whole bunch of abstraction that is inside your source code. And this abstraction is really what is most interesting. So reverse engineering. Reverse engineering is the process, like the inverse process of engineering. And perhaps in order to understand this better, we should say what reverse engineering is not. Because reverse engineering is not disassembly. In the sense of that, well, the source code is not everything that is produced in the engineering process. We have all the abstract design, we have all the higher-level concept, we have the relationships, and so forth. The source code is the end product. And the disassembly is not even the source code. So the disassembly does not do anything to actually reverse the engineering process. We just get, well, some assembler code which we can then try to understand. So the end goal of reverse engineering is not to get a clean disassembly or to have a good disassembly or whatever. Of course, you need a good disassembly to really start the reverse engineering process. It's like the first step. But this is not the end goal. And basically, a good disassembly should recover you all things cleanly that you can easily recover from the executable, meaning all the function boundaries, which basic blocks belong to which function, and yeah, that's already it, more or less. Like, that's what the disassembly process should really be giving you. And you should measure your disassembler by its capability of doing that core competency, getting you a clean, good disassembly which groups all the instructions belonging to a function into that function. All right, so what else is reverse engineering not? Reverse engineering is not decompilation. There's a bunch of reverse engineers that I know that think that the end goal of any reverse engineering process is producing code that is recompilable into the same binary. And I strongly disagree on this, because if I give you the source code to Oracle now, you don't understand crap about it. If I give you the source code to Vista now, you don't understand crap about it. Microsoft doesn't understand the source code to Vista, I'm quite sure. I don't think anybody does. So the thing is that decompilation to source will help somebody who doesn't know assembly to reconstruct the higher level abstractions. But it doesn't change the fact that it is really not the end goal of reverse engineering. Because what is the end goal of the reverse engineering is the recovery of the higher level abstractions. All right. So the thing really is that source code itself, when just recovered from a binary, does not help really. Okay, it helps people that are not fluent in reading assembly language. It helps people that, well, to an extent, it might help me read code or whatever, or other people that are just not very good at assembly. But in the end, it's really not the goal to get source code. So the really broad definition of reverse engineering has to be that we want to recover high-level abstractions, meaning, well, we want to basically get all the things from the executable that normally a good and clean design process or engineering process would create, meaning modularization, interfaces, how the components fit together, which components are responsible for what, and so forth. Essentially, reverse engineering should be able to generate, given only an executable, a full documentation of the program and, well, diagrams of how things relate and so forth to make it easy to understand the system. All right. Of course, in this select audience, bug finding is usually the goal. But if we really think about it, realistically, in a few years, I don't know whether it's going to be 5 or 20 or 50, there won't be overflows anymore. Static analyzers are getting very, very strong. The A340 avionics code was proven to be free of out-of-bounds memory access, and that's a significant chunk of code with multiple threads and everything. So we can just say that at some point there won't be the silly overflows or the silly we write out-of-memory thingies anymore. At that point, it comes down to logic bugs. And logic bugs are fiendishly hard to detect automatically and can be detected if somebody understands how the components fit together. So for us as people who are looking for bugs in the long term, we just have to understand massive amounts of the program, or massive parts of the program. If you ever have the chance to speak to Mark Dowd, he's got a very, very interesting perspective on this, because when he looks for bugs, he really understands most of the program first before he does most of the auditing. By the way, Mark Dowd and John McDonald are writing a book on source code review, and it's excellent. If you happen to have your book budget empty, or still book budget available, go and buy it. I'm not getting paid for this, it's just a good book. All right, so the question is, how would we even start to recover high-level structures, like the high-level concepts in an executable? Because when we have the disassembly, all we have is like this big chunk of functions and how they relate in calls to relationships, and we got nothing else really. So perhaps we should start by asking ourselves, what is a piece of software really? And I'm horrible at designing diagrams, so this looks all marketing crap and totally meaningless. But in essence, a program, first of all, consists of modules. Like you have the module responsible for doing the network interaction. You have the module responsible for doing something else. You have the logging module. You have the allocation module, and so forth. So an application consists of a bunch of modules. All right. And each module has a structure in itself, because a module is usually designed that you have an external interface, functions in that module that you can call, and then you have the internal functions, which are being then called from the external interface, and you have external data structures, meaning data structures which the module uses to interact with the outer world, and you have internal data structures. So one of the goals that we would need to have in our reverse engineering tools would be to, well, take an application, separate it into modules, and then for each module, identify what the external interfaces are, identify what the internal functions are, identify what the data structures are, and which ones of these are used to interact with the outer world. All right. This is basically, if you look at software from a non-object-oriented paradigm, which means, well, if you ever try to look at embedded VPN appliances or routers or whatever, you really get these huge, insane systems where you have no concept of modularization from the disassembly. And this is really where this, this question is coming from, because under Windows you at least get like multiple DLLs, which gives you an approximation of modularization. So in general, it's interesting to read books on proper software design. Well, the Dowd McDonald book is not on proper software design, but on bug finding and bad design, but still. And they define a few things that are important about modularization. Specifically, the modules of a program should exhibit loose coupling, meaning they should have very few well-defined interfaces that sanitize input coming in, and they should have strong cohesion, meaning they should do a set of very tightly related tasks. All right, so the question is, can we recover from the executable modules in a manner that they exhibit, well, loose coupling and strong cohesion? We're a little bit luckier in the object orientation or in the object-oriented paradigm, because if we can reconstruct all classes from an executable, all the inheritance relationships and so forth, we get a large part of the abstract design from that application automatically, just because we have objects which are directly connected then, and so forth and so forth. So actually I think that recovery of the abstract design is easier when you have object-oriented executables, just because you get more information about the design in the executable in the end. If you just compile ANSI, you just get a bunch of functions, whereas in the object-oriented model, you get classes, inheritance relationships, and methods which belong to one class but not to another, and so forth. You get the functions already grouped by functionality by operating on the same class. All right. So the thing is that reverse engineering has historically been mostly done in secrecy and only by a very small number of people. That has changed significantly over the last years. I mean, the sheer fact that we have this many people in this room shows that reverse engineering has grown and matured quite significantly over the past few years. And the thing is that on the engineering side, we have tons of advanced tools. Like we have UML diagramming and generation of code from UML diagrams, and then regeneration of diagrams from existing code, and so forth. On the reverse engineering side, we're a bit stuck in the 80s. Like, we have IDA, and IDA is good, is an excellent disassembler, but it is really not doing any of the higher level things. And well, we don't have all that many other tools. Now, the tool side is changing very slowly now. We are getting a few other tools going. There's a HB Gary's Inspector, there's PyMay, there's BinDiff, there's BinNavi. But to be quite frank, all these tools have a user base of probably, well, I know that BinDiff has a user base of a bit more than 200 people, I guess. Everything else probably has a user base of below 50. And that means that they're extremely tiny in their reach. So reverse engineering has grown, and apparently there's budget for it, otherwise most of us wouldn't be here. So perhaps at some point we can actually afford some real R&D into reverse engineering, meaning solving a bunch of problems that we really should be solving. So what will follow now is my wish list of problems that should be solved or that I would spend my research money on if I had any. So I hope there's people in the audience that have research money to spend it on. And also I'll volunteer. If you want, you can spend research money on me, and then I'll do the research. But all right. Thing is, with almost all the problems you'll run into here, almost all of them will be, in the worst case, undecidable, in the better case, NP hard, and all this, of course, speaking about the general case. So in general, everything that I propose here will be either undecidable or NP hard, but the thing is that you never meet the general case in real life. You always meet special cases, and for most NP hardness proofs,